respected Chief Guest of the Day, Mr. Karthik Goyal, Application Engineer, Jyoti Electronics, Ahmedabad, my dear colleagues and dear participants, good afternoon to you all. Today, I am really proud to be here in front of you as Head of the Department of Electronics and Communication Engineering Department, Jyoti Engineering College. This is a department that has grown from year to year and still marching forward. We have been accredited by NAAC and accredited and re-accredited by NPA, the prestigious academic boards of accreditation in our country. This webinar on antennas in biomedical application and MIMO technology is jointly organized by Electronics and Communication Students Association of Jyoti Engineering College, Institution of Engineers India, IEI of Jyoti chapter, and Jyoti Electronics, Ahmedabad, Gujarat. I am very grateful to Mr. Pradeep Agarwal, the Technical Director of Jyoti Electronics, Ahmedabad, Gujarat, for giving us all the support for this event. Now, to my very pleasant duty of officially welcoming you to this webinar. First of all, Mr. Karthik Goyal, Application Engineer of Jyoti Electronics, Ahmedabad, who has taken time off from his busy schedule and available here as a speaker of this webinar. I welcome you, sir. I also will take this opportunity to welcome Dr. Prajun and Mr. Dr. Panmani Raja, Assistant Professors of Jyoti Engineering College. They are the main coordinators of this program. I welcome you both to this webinar. And now I must turn to the participants of this webinar. Without you, this function would be meaningless. I welcome you all to this function. Welcome once again to all of you. Thank you.
Thank you, sir. Today for the webinar, we have Mr. Karthik Goyal with us. He has completed master degree in microwave engineering and bachelor's degree in electronics and communication engineering from Dr. APJ Abdul Kalam Technical University, Lucknow. Post PG, he was associated with SRMS Trust Institution as assistant professor for almost 4 years. He has presented and published multiple research articles in national and international conferences of high repute. His area of researches includes RF and optical antennas, plasmonics, photonics, microwave photonics, and communication systems. Currently, he is working as an application engineer at Jyoti Electronics, Ahmedabad, and has a specialized hand in CST MWS used in microwave domain. Also, he uses to work on the queries to provide technical support from SAC, ISRO, DRDO, and from all research scholars doing ample of work at different premier institutions of India. He is also an active content writer and trainer in the fields of RF and microwaves. It is my pleasure to invite you, sir. I invite you to move on with the session.
Thank you, ma'am. Thank you very much for such a nice introduction of mine.
Thank you.
I'd like to thank HOD Department, Jyoti Engineering College, Kerala, for conducting such a webinar during this tough time of pandemic, COVID-19. I also thank Dr. Prajun and Dr. Panmani Raja for inviting me to deliver the talk on antennas in biomedical and MIMO technology. I also welcome all the participants who have joined us from all parts of the country in this webinar. I also like to thank Mr. Rajendra Agrawal, the Managing Director, Jyoti Electronics, and Mr. Parth Agrawal, Director Technical, Jyoti Electronics, for allowing me to deliver this talk. So, I'd like to seek permission from Dr. Prajun and Dr. Panmani. Should I start sharing my screen, sir?
Yes, sir, we'll start.
Okay, thank you. So, is my screen visible completely to all the participants? Kindly acknowledge.
Yes, sir, it's visible. Yes.
Yeah, okay. Yeah, okay, great. So, a brief introduction of mine has already been given by the coordinators of this particular webinar. Let me introduce a bit of my organization to which I work for. Jyoti Electronics Ahmedabad. Actually, we are into the business of techno trading actually from the last 35 years, and we have diversified our all energy into the fields of RF and microwaves since 2000. We are into everything that you people can think of at the RF and microwave domain, either it is related to hardwares or related to softwares. We are the main channel partners, or we are the sole channel partners of Dassault Systems that owns one of the most promising platform into the domains of RF and microwaves called CST Studio Suite. I won't be talking about this particular platform today, but although we'll be using multiple of its materials for justifying my words during the session. And yes, again would like to thank Institution of Engineers India as well for collaborating with Jyoti Engineering College and Jyoti Electronics for this particular webinar. So since I am a microwave engineer, so I usually feel this thing actually, that whenever I talk technical into the technical aspects, or whenever any microwave engineer talk into the technical aspects, two things happen. Either the entire audience fall asleep because they won't be getting anything, or they will be amused to know that yes, this is something which can change the scenarios for us in a very short span of time. If we start working on this, this can take us to a different level. Our research will be taken to a different level, and the technological advancements could be made. So yes, this is the quote when I was there in IIT Kanpur during an FDP along with Dr. Ponmani Raja, the Professor Animesh Vishwas. I used to say, quote this line that microwave engineers only have the capability to either make a group fall asleep or take them to the wonderland. This was the day from where I and Dr. Prajun, Dr. Ponmani Raja are in collaboration. I'm working in very close proximities since 2012, I guess. So without wasting much of the time, let's start today's talk on the antennas in biomedical applications and MIMO technology. This will be the content for the talk. I will be discussing a very basic concepts, very basic points, and very basic key features while we go for some research scenarios, either in biomedical applications or in for MIMO technology. Since when I talk about MIMO technology, it again considered two aspects. The very first one is for LTE or 4G applications, and the second one is for 5G applications. There is a very minute thin line difference between the MIMO antennas for 4G or LTE applications and the MIMO for 5G applications. You can see there is a word mentioning that MIMO technology for LTE, and thereafter I will be introducing a term MIMO technology. So this M would be creating a massive difference between the 4G and the 5G technology. I will be discussing and giving you the glimpse of everything during this particular session of, I guess, 1 hour, or we will be extending it to some within the time constraints. So very basic introduction. You may see that yes, as the wavelength or as the frequency varies, as the wavelength gets smaller or frequency gets higher, then the role of the humans, then the role of the smaller particles, the role of the atoms or nuclei comes into the play. As soon as you increase your tends to increase your frequency, this sort of nuclei could be taken into the considerations. At few of the megahertz or few of the terahertz, the complete human structures can be analyzed. So this is the very general scenario everyone is aware of, since we all belong to the domain of electronics and communication, and few of us are already working into the domains of microwave engineering and RF engineering. So yes, this is very relatable with everyone. Then why do we go for microwaves? What are microwaves actually, and why do we go for it? So here are the few reasons, few generalized reasons that why have we opted microwaves to work on. Because as the technological advancements are taken into the considerations, there is the need that a particular radiation region must increase. So microwaves have the more radiation effects. These have the more heating effects. So yes, one of the main reason to have the microwaves into play. Thereafter, yes, as we increase the frequency or as we goes decreasing the wavelength, that is, as we tend to move towards the microwaves, the electrical size of the structures tends to increase, while without making any of the changes in the physical structures. The physical size would remain the same, but rather we would vary the electrical length or electrical size of the structures. So this would be one of the other reasons. Then one of the major reason is it is very advantageous for imaging aspects. When I talk about imaging, then yes, these provide us the best images of the inner parts of the human body, the inner parts of the heavy structures. We can create or we can have the proper imaging, right? So these are few aspects where we tend to use the microwaves, or we are forced to use the microwaves to consider all these aspects into the consideration. So these are the different areas where the microwaves are being utilized in current scenario. And as far as I am concerned, whatever area you pick, you cannot leave it without, or you cannot work into the domain or into the region without microwaves. Either you talk about the communication tools, you talk about the wireless technology, you talk about the IC designs or signal propagation, you just name it, and yes, I'll justify the need of the microwaves into the particular scenario. So RF designing and microwave engineering is applied to every different aspect of life nowadays. So since the theme of the session is antennas for biomedical applications, and yes, of the MIMO technology, so let me introduce few of the basic parameters you might be aware of. Yes, definitely you might be, you are aware of all these parameters, that what are the general antenna characteristics. So in terms of input, when I talk about input, then yes, input impedance would be the major one. What is input impedance? What's the role of the input impedance? That you try to feed, and you feed an antenna. When you try to feed an antenna, then there should be some impedance matching. So there are two aspects of the impedance matching. The very first one is that whatever the port, or whatever the excitation, or whatever the feeding technique you are using, that particular excitation port must have some impedance. So whatever be the impedance of that particular excitation port, it should match with the geometry of the antenna that you are feeding to. That means, let us suppose a basic rectangular patch having inset feed mechanism. So when I talk about the matching term, it means the port that I would be using, suppose it is having an impedance of 50 ohms. So the feeding line that you have created should also have the impedance of 50 ohms approximately, in order to have a proper matching, in order to have the best performance of the antenna, or you say in order to have the minimum reflection coefficient, right? So this is one of the important aspects when I talk about antennas, input impedance. And the second one is impedance bandwidth. That is, up to what particular bandwidth your impedance is matching. This will be another greatest parameters while I talk about the input characteristics of antenna, right? Thereafter, the few of the important parameters which are in terms of radiations only, although apart from radiation there are ample of parameters, but yes, for advanced sort of antennas, these radiation parameters are very important. And out of these, the very first one is field patterns. That is, you must know that how your electric field vector and how your magnetic field vector are varying on the structure. Because with the study of the electric field vector and the magnetic field patterns, you will get to know the orientation of electric field, and which I call the polarization, right? And with the help of these field patterns as well, you will get to know the modes, that how your propagating modes are varying, how the number of cycles, or you say when you designate it as M, N, or P, how these particular values of M, N, and P are varying for individual structures. So these are the things that can be related with the field patterns when you go for the visualization of such things. Similarly, for the higher frequencies, what your current pattern is one of the thing that would be taken into the considerations. Power patterns as well, that how your power flows or how your power varies within the structure. You can completely visualize these things while you go for the simulations. Thereafter, few very important parameters of both are interrelatable with one another: gain and the directivity of the antenna. You all know the basic definitions of these two parameters, but yes, I'm not saying that these are the parameters that are important for every sort of antenna. There are ample of class of different antennas, and yes, it may be the situation that for few antennas gain is very important and for few gain is not. So when I talk about few of the antennas in terms of biomedical applications, then yes, gain for few of the biomedical antennas is not important. Directivity is not important. Rather, what is important in terms of biomedical applications, that what sort of power loss density is there. If you put some antenna on the wrist, on the shoulder, on the neck, then in these scenarios, your power loss density comes into play, and this particular parameter, power loss density, will be the most important one, because this is the parameter that will provide you the specific absorption rate, SAR. You might be aware of SAR parameter. It is one of the parameters that we look for while we working in the biomedical applications. Similarly, this particular polarization, yes, while this is one of the greatest parameters while I talk about CP antennas, circularly polarized antennas. We may use CP antennas for our biomedical applications in some cases. Yes, we can use. So polarization is one of the greatest parameters. Either your antenna is possessing LHCP characteristics or RHCP characteristics, left-handed circularly polarized or right-handed circularly polarized. Either it is elliptically polarized or it is linearly polarized. So yes, polarization is one of the parameters. And how we can have the polarization? By the study of axial ratio. We must know the value, we must know the characteristics of the antenna in terms of axial ratio, so that we can justify the particular parameter polarization. And similarly, the pattern bandwidth would be working for you. So these are the very important parameters. I'm not saying these are the only one. There can be a few, like for the basic antennas, there could be some VSWR, there could be some scattering parameters, right? There could be some Z parameters. So yes, multiple different parameters are here, but for today's session, these are the few which are very important to know. So these are a few classifications of antennas at biomedical applications. Very few classifications of such things. The very first design, this particular structure is having a RFID tag at the wrist of the human model. This second structure is having some implantable antennas on the human body. The third one is having the analysis of a mobile phone in different modes. It is in calling mode. This one is reading, and this one is reading while connecting with the Bluetooth or while connecting with the Wi-Fi. So these are few of the cases for antennas for biomedical applications. If I talk about this particular mobile phone, then yes, it would be having multiple sort of antennas. What would be these antennas? Either it would be the antennas for cellular communications. When I talk about cellular communications, then yes, I need to consider both the frequencies, the 900 megahertz and 1800 megahertz for GSM. Yes, when I talk about a mobile phone, there may be a case that some Bluetooth connectivity is being used. So that is what for that for ISM band we need to consider the mobile phone. Yes, again for Wi-Fi applications we need to consider the mobile phone. So yes, there are multiple aspects a mobile phone could be used. So in every terminology, either it is Bluetooth, either it is Wi-Fi, or for cellular communications, your SAR would be working. Your antenna would be radiating. Your antenna would be radiating a bit in order to have the specifications, or in order to have the impacts on the SAR analysis on the human body. So these are very few examples of biomedical applications. Now, here one thing is very important to understand, that what are the biomodels? It could be, let me give you a brief on this as well. It could be a CAD model. Once you are using a CAD model to analyze your SAR performance of any instrument that you have designed, in that particular scenario, you won't be able to check the proper implications, the proper impacts of the instrument on the inner parts of the body. And when this is one of the class of the human models as CAD models. The very first one, this particular wrist hand model is the CAD model only. While this particular human model in the second figure is complete human biological model. When I talk about the complete human biological model, then yes, in this particular human biological model, there would be the consideration of heart, there would be the consideration of lung, there would be the consideration of kidney, there would be the consideration of brain, blood, arteries, veins, everything would be considered in a human biological model. So there are two classes. The very first one is human model, and the second one is human biological model. So there are two different aspects I need to know when we go for the simulations or when we go for the exact physical environment. So while I go for the performance of the antennas in biomedical applications, again, these would be the parameters that would be playing an important role. The very first one is everyone models our structure very easily. The case stucks, or the researcher stucks in between when it comes to the type of feeding we need to put. Feeding mechanisms is one of the major design constraints that we need to know about in biomedical applications. There are various feeding mechanisms in terms of simulations I am talking about right now. The very first one is we can assign some discrete ports. We can assign some aperture coupled feed. We can assign some coaxial probing. We can assign some inset feeding. So there are multiple feeding mechanisms that we can use. But yes, we need to know that which one will be working appropriately for my structure. Like suppose if you have implemented, let me get back to the previous slide again. If you have implemented this RFID on the CAD model or on the hand, then it is on the upper surface, right? Although the structure is of antenna, but this is an RFID tag that you can put it on the wrist and you can go anywhere. Then it won't be the case that you can connect it or you can excite it using a coaxial probing, because you cannot take the probe everywhere. So for that particular reason, we can use a discrete port. This is one of the consideration that we need to take in, that either we are creating an antenna or either we are creating an instrument for the mobile reason, means for the mobility purpose, or the user would be moving using that particular instrument on the body, or the user would be sitting at a one place. So keeping this particular constraint, we can pick our feeding mechanism. The second one is scattering performance. Yes, this is one of the major parameter that comes into play. Scattering performance, when I talk about, that means the value of return loss or the value of reflection coefficients. So again, let me introduce from this particular design only, that when I apply this RFID, when I implement this RFID on the human body, then just imagine the top surface, this particular top surface on the cursor is moving, would be having some radiations in the space, in the environment. Also, since you see, you need to visualize it very deeply, that there is no any substrate under it. There is nothing under it except this hand model. That means there would not be any ground plane as well. It would not be containing any ground plane, any substrate, nothing it would be containing. That means since we have eliminated the need of the ground plane, that is why it would be radiating in the back directions as well. There would be multiple back lobes. So these particular back lobes are generated. That is why your scattering performance would be degraded, because we use the ground plane in order to divert or in order to force the energy into a particular direction in the forward one. And since we have eliminated the ground plane, then yes, there would be some back lobes. That means the reflections are there. And when reflections are there, it means your reflection coefficient would be high. That means your scattering performance would degrade. So this is one of the major parameters that you need to analyze very appropriately, that for what applications we are creating, and depending on the application, what could be the scattering parameters. Again, there would be a comparative analysis. Yes, since you are doing or you are creating an instrument or an antenna or anything to be put on biomodel, then you need to do the comparative analysis along with. You create an antenna, you simulate it, you work on that, have the results, then put the antenna on the human model or anything, and thereafter you compare the results, whether there are some difference in the results or not. If there are some difference or some vast difference, then you need to reconsider your designs again. Or if they are comparatively same, then yes, you can move further. Then similarly, this is the parameters that I have already talked about. The gain, the current patterns, power loss density in terms of biological models I have talked about, and this power loss density would be playing the role for having this particular parameter specific absorption rate. Right? So these are the things that you can you need to consider while you go for the designs. So this is the thing that we have created to demonstrate for you guys. When I talk about biological models, then you can see this is the pattern for SAR. This is the pattern for power loss density, and having the value of the red one, the reddish one is having the value of 5.27 watt per kg. So yes, this particular RFID tag has been placed. You can see this particular RFID tag has been placed on the rest of the human model, and this is degrading. This is having the performance in terms of SAR like this. This is the color band of this particular pattern. You can analyze this pattern using this particular color band. So what we can analyze it, that 5.26 watt per kg is the SAR, is the power loss density in the back direction, and that is the value by which your human CAD model is being affected using this particular RFID. And this is what, this is surface current. This is what, this is surface current of this structure. And you can see this particular surface current is only having the arrows on the structure, only on this meandered structure. This is what we call meandering, to change the electrical size of the antenna or the structure without varying its physical aperture. So this is meandering. So these are some of the results. Now, this is another project of having the SAR analysis of some human model, human head, and a mobile phone. Now you can see this is a human head, this is a hand, and this is a mobile phone. And what have been mentioned in dark, all these are the different antennas for different applications. You can see in the complete structure, there are multiple things that are being used. That for the body, a hand and a head is used. For the phone, some antennas are used, some batteries are used, some cameras, connectors, some body of the mobile phone, some PCBs, and some screens are used. So out of the antennas, we have some cellular antennas, we have some Wi-Fi antennas, we have some basic general purpose antennas, for some Bluetooth antennas. So all these are the antennas that you can see in the structure. These all are the antennas. So you need to figure it out that there is one more consideration which is very important to know when I talk about biomedical applications. When I talk about antennas for biomedical applications, there is one of the major considerations is that you need to keep an appropriate distance in between the instrument and the human body. This is as per IEEE. You need to keep an appropriate distance in between the mobile phone or in between the instrument that you have designed or in between the antenna that you have designed and the human body in order to restrict the direct impacts, right? So in this particular design, we have also used an appropriate distance of at least 5 mm in order to have the appropriate analysis. So now let me brief you on this as well a bit more. In this particular structure, in this particular design, we people have used 6 antennas, 6 different antennas. Likewise, a few are using for 900 megahertz, few are being operated on 1800 megahertz, few are being operated on 2.45 gigahertz, few are operated on 2.55 gigahertz. So first we tried to figure it out that what are the scattering performances of different antennas. So these are the scattering properties of different antennas working at different frequencies. You can analyze with the color codes. These are on the general scale. So these are the scattering values of different antennas. So for me, these are not very important. These are not really very important for me. What is important for me is the calculation of SAR values, which is very important for me. So let's have a look. This is the calculation of SAR or the chart of the result of the SAR at f is equals to 0.9 gigahertz for the antenna number 1. And the standard was taken as per IEEE standards, and the averaging mass value was 10 per 10 grams. We have calculated this SAR per 10 grams of weight. You can calculate it per 50 grams of weight, you can calculate it per kilogram of weight, or you can calculate it a point SAR as well. You can calculate a SAR at a particular coordinate or at a particular point. So this is up to you. This is up to the flexibilities that the platform you are working on is providing to you. And this is the results we have calculated or we have obtained using, you can see, CST Microwave Studio. So you can see here that the maximum SAR per 10 grams in the units of watt per kg is 1.49771 due to the presence of the antenna number 1, which is being operated at 900 megahertz. And the minimum value would, yes, obviously be 0. And what is the maximum volume at which this particular maximum value of SAR is impacting is this particular volume. Maximum at this particular coordinate, it is having the maximum value of this 1.49771 watt per kg. So these are different type of results you can have from different platforms you are working on, and this is one of the results. Similarly, I have another result. This is again the result of antenna number 1 if it is being operated at frequency of 2.45 gigahertz. Now you can see due to the change in the frequency, operating frequency, the SAR has been changed and it is now 2.55033 watt per kg. And again, averaging mass is per 10 grams. So you can have multiple results using different platforms. And since this particular result is again carried out using CST Microwave Studio. So this was a brief about the antennas for biomedical applications. You can work on implantable antennas. You can put antennas into your inner core of the body. You can put an antenna on your heart to analyze its different parameters. There is one more thing in the biomedical applications, that once you have the complete biological model, now I'm talking about biological model, not human bio model. I'm talking about the human biological model. When I say biological model, every different aspect of the body, every individual parameter, every individual component, every individual material in the body would be considered. So you can suppose you need to have some analysis on a patient who is having some sugar, who is having diabetes. So their blood considerations would be changed. It would be having different blood properties. So yes, you can change that particular blood properties from the material libraries of any of the platforms you're working on. I don't know about regarding the other platforms, but yes, CST has that particular flexibility that you can change the material properties of the blood, you can change the material properties of the arteries, you can change the material properties of the lungs or kidneys, or everything you can change. You can customize accordingly and you can work on. So this is the flexibilities that you may have while you go for the simulations before going to the actual practical scenarios. Now, moving further towards the MIMO technology, that is very important. MIMO, as the name suggests, multiple input, multiple output. That means at the transmitter and the receiver, you can see there are multiple antennas, and all are sending or receiving some signals simultaneously. Now, there are two considerations. Actually, two technologies are running in parallel nowadays who are using MIMO antennas on a very large scale. The very first one is 4G or LTE technology, where your Wi-Fi routers are into the existence. And the next one, which is a very few countries are using, the latest one is 5G technology, or some what are using some 6G technologies as well. So there is a very thin line difference between the 4G technology and the 5G technology, or the antenna advancements in 5G or 4G. And that particular variation is given by this particular letter. This particular letter M is making the entire difference in 4G and 5G. So we'll discuss on that as well in a while. So this is the MIMO technology concept of MIMO technology, that both the transmitter and the receiver would be having same antennas, would be having same number of antennas, and each would be transmitting or receiving simultaneously. Now, there might be, let's just try to understand the concept of MIMO. The very first thing is, whatever be the number of the antennas at transmitter or receiver, that number of antennas should be the same. The very first thing is, number of antennas should remain same. The second concept is, whatever be the number of antennas you are using in your design, all the antennas should be identical to one another while I talk about 4G technological concepts. Mind it, keep into your mind that all the antennas should be identical to one another when I talk about the antennas for 4G MIMO technology. When I talk about the identical nature, it means the design should be the same, appropriate exactly the same, the feeding mechanisms should be the same, the input amplitude should be the same, the phases or phase shifts in each of the elements would be the same. Then only your antenna or the structure would be called the antenna, that yes, your structure has been designed or would be implemented for the 4G MIMO. I don't know whether you have seen or not, while you try to figure out that how does the radiation pattern of a Wi-Fi router looks like. Have you ever seen the Wi-Fi router radiation pattern? It looks like the shape of a donut. Yes, the one that we used to eat, donut, a very tasty one. So it has the shape of that particular donut, Wi-Fi router. Why is it? Because each of the antennas that has been implemented on the router are having the same radiation properties, are having the same characteristics due to the identicality in the shapes, due to the identicality in the structures. So these are the few challenges that are there in the design of MIMO, either it is 5G or 4G. The very first one is the size of the structures. Since we are at the highest frequency range, we are at the microwaves, then it means your electrical size would be large, but your physical size would also be a consideration. So we need to keep it as compact as possible. And the second thing is the mutual coupling between the antennas. Suppose if you are using a 4x4 square matrix of the antenna, then there should be the interferences between each of the elements. Since antenna 1 is radiating, antenna 2 is radiating, antenna 3 and 4 and antenna up to 16 are radiating simultaneously at some frequencies, and all are interrelating or all are interfering with each other. Then yes, loss of energy would be there. So you need to consider the concept of mutual coupling into the play. This is one of the greatest parameters while you work on MIMO technology, mutual coupling. And how you can control this particular mutual coupling parameter? By keeping the two concepts into the mind. The very first one is polarization diversity, and the second one is spatial diversity. When I talk about the polarization diversity, what I mean to say? I mean to say that how you place your antennas, say whether it is like that all your antennas are placed vertical to each other, or all your antennas are placed horizontally, horizontal to each other. It should not be the case. For 4G technology, for 4G LTE communication systems, equal number of antennas should be placed in horizontal and vertical directions with reference to a single antenna in order to have a proper donut shape of the structure of the array. That would be the case if you are having equal number of antennas in each of the directions. Then only your antenna would be radiating in each of the directions. So we should say it would be having a pattern of some omnidirectional shape. That it would be present. It would be radiating in each of the directions equally. This is one of the considerations that we need to take. That is polarization diversity, and second is spatial diversity. It is another important parameter. When I say spatial diversity, yes, I mean it in regards with space of the antennas, spacing between the antennas. Your antennas must space like none of the region would remain unused. When I talk about the omnidirectional pattern, then your antennas should be placed or should be spaced with one another like the way that your radiation pattern of individual antennas would cover each of the space very efficiently, very equally. And none of the space would remain untouched. So these are two very important parameters. And once you consider these two parameters, just focus on few of the parameters to justify the performance of MIMO antennas for 4G applications especially. The very first one is envelope correlation coefficient. This particular parameter is directly related to the mutual coupling coefficient or mutual coupling concept, right? Your envelope correlation coefficient would be directly related to mutual coupling concept, and it means that lower the value, your antennas are not mutually coupled, right? Theoretically, its value should be below 0.5. Means it is considered that if the 50% of the mutual coupling is there, then it is an issue, but below 50% it could be considered. But you need to focus that it should be as below as possible. I'll show a few of the designs right here. Thereafter, again, few of the parameters: diversity gain, mean effective gain, very well written in standard books. And for me, the ECC is one of the greatest parameters to justify the need of the MIMO antennas in terms of 4G applications. So you can go through all other parameters well written in the books. I would not be focusing due to the time constraints. I was only allowed to have a time session of 1 hour, and it's about to over. So I would be discussing few of the important things right now. So yes, this is one of the design of the unit element of the MIMO technology for 4G applications. This is a C-shaped monopole antenna. C-shaped monopole antenna that was designed, that was tested for 4G applications, and once it was tested with the unit element, we tried to modify it in this 2x2 matrix. You can see now these two elements are placed a much more wider, with a wider space than these two elements. You can clearly visualize that there is a much more greater spacing between element 1 and 2 than in between element number 1 and 4. And element number 1 and 3 are placed in different polarization with one another. These element number 1 and 2 are placed in different polarizations. You can see these are in different polarization, and these two are in different polarization, and these two are in different polarization. So this is the thing when I talk about the polarization diversity and the spatial diversity. So let me show you the performance of using a single element, that this particular element, and after this 2x2 matrix. What is happening actually? Once you convert a unit element into an array, then obviously the performance of the design would increase. Yes, it would increase by different aspects. If you are feeding or if you are having some identical antennas, then only their performance in terms of scattering parameters would increase. Rather, there would be a very smaller, very minute level of advancements or modifications or enhancement, I should say, enhancements in the directional properties. But yes, in terms of scattering properties, there would be a drastic change, as you can see here in this particular design, in this particular graph. You can see the red one is for the single antenna, while all these four graphs, S11, S22, S33, S4, these are all the similar ones. They are just equal to one another. Since why these are equal to one another? Because all these four elements were very identical to one another. Since the elements were identical to each other, therefore their individual reflection coefficients would be identical to each other. But when you go for the isolation losses, then yes, you would get to know that the isolation between antenna number 1 and antenna number 2 would be the same as that of the isolation between element number 3 and element number 4. But the isolation between element number 1 and 2 would not be matching up with the isolation between 2 and 3 because of the different polarization schemes that have been implemented. So these are the concepts of polarization diversity and spatial diversity or pattern diversity. You can go through the slides. I have already discussed that this much in detail also with this particular graph. Since all the elements are identical to each other, therefore these are all having the same return loss performance. And now you can see there are few differences in the isolation losses. You see the isolation between element number 1 and 2 and element number 2 and 3 are same. This particular black one, and over that you can see a different color. These are the same, but element number 1 and 2 and element number 3 and 4 are having some different isolations, and element number 4 and 1 would be having some different isolations. So this thing happens just because of the fact that how do you place your elements? Element number 1 and 4 would be having the same isolation as element number 2 and 3, while element number 1 and 2 would be having different isolation in comparison with 2 and 3. So this thing you can visualize here in the graph. Now these are the return loss. These are the radiational patterns, radiational properties of individual 4 elements. Element number 1, element number 2, element number 3, and element number 4. You see, all the elements are having same sort of radiation patterns with the same value of directivity, 3.02 dBi. All the 4 elements are having the same radiation properties in terms of directivity. Although there are a few rotations in terms of the directions. You can see all the 4 elements are rotated. This is the radiation element number 1. So this is now quite rotated for element number 2. And again, this particular has been rotated for element number 3 like this. And this again rotated by an angle of 90 degrees by this. Just because of the fact that all the antennas are oriented differently. Now, when I try to combine all these 4 into a single radiation pattern, as I say, the shape should be of a donut type, then yes, this would be a shape. This would be a shape of the 4 combined elements. And yes, your directional properties, your directivity has been enhanced up to 3.22 to 3 dBi. When we have combined all the 4 radiation patterns, your directivity has been enhanced up to some level. Your shape of the radiation pattern has been touched up to the perfect one. It is some sort of a donut shape. If it is in presentation mode, if it would be a software, then I would have shown you that how beautiful it is of donut shape. So this is all when I talk about the antennas of MIMO technology for 4G communications. But as soon as I enter into 5G communications, the things gets changed. Since the word is this is another concept of mutual coupling in MIMO. All the 4 elements would be radiating in a different pattern. In a different pattern, you can see this element number 1 is radiating this way, while the element number 2 is radiating this way. What this particular slide is showing that each of the individual element, if I consider, then each would be radiating in a same manner, while all the four elements, if I talk about on a whole, on a combined, all these four would be radiating very similarly. You can see all the four elements are radiating simultaneously with the same sort of plot. You can just visualize the same sort of plot. It would be radiating simultaneously. This is the plot of the surface current having the maximum value of 13.4 ampere per meter. With the as per the color plots of reddish red one, this red at the boundaries, these are the excitations that have applied to the individual antennas, and this red within the structure of the antenna, this is the flow of the surface currents. So this thing would not be the same when I talk about 5G technology. This thing is not the same when I talk about 5G technology. This is MIMO technology, the massive MIMO. When I use the word massive, this is the differentiator between 4G and 5G. Massive means on a very vast level. That means there would be a very large number of antennas at the transmitter and at the receiving end. So what is here in communication? What is at the receiving end? We as the users are at the receivers, and our base stations, our service provider stations are the transmitters. So since the users are increasing rapidly, then yes, there would be a need to increase the number of transmitters or number of transmitting antennas at the base stations as well. So yes, you can see the more active elements, antenna elements would be there. And as soon as you increase the number of elements, then yes, more focused energy would be there. And now this is the less interference. This is the thing that we will be looking for as being a designer. As being a designer of at the microwave frequency or at the RF frequency, it is our task that we should have the more focused energy with the less interference. Right? So we are here to focus on this particular thing. So what is the prime concept? That each of the individual antenna would be radiating, would be having some focused energy to each of the individual user. As you can see, each of the individual antenna would be having more focused energy for each of the individual user, or I should say each user has occupied a fixed antenna that my communication would be done using this particular part of the antenna, with this particular antenna element only. So for this, there is a concept called beam forming is there in 5G technology. This is something what I call about beam forming concept. You can either visualize or let me explain this beautiful concept of AM technology, right? So this is the very single radiating element, fed with a single source, having some radiation pattern, fine, no issue. This is a single element. But as soon as we increase the number of elements, let us see what happens. In the second is this part, there are two radiating elements, all are fed with the same source. You can see a single source was coming and now is being diverted to both the radiating elements without any external use of any phase shifter. Mind it is very important to mention here that here we haven't used any sort of phase shifter in this particular division of the feeding power. So your radiation pattern is somewhat more focused. You can see initially it was forming a sort of hemispherical shape. Now it has formed a sort of a balloon shape. And if I try to create more number of elements with the single source again, then yes, your main lobe or main energy is being directed with much more focused beam. While there are few side lobes, few losses are there, yes, but your main energy is being directed with a much more focused beam. This is very important. Thereafter, now the scenario is changed. What the new scenario is? Yes, again I have two elements as in the previous case. This was the case, two elements. But now both the elements are fed by two different sources. Now two different sources are being used. Then yes, each of the source would be putting its impact, and there would be two radiation patterns. The radiation pattern for first element and the radiation pattern for second element. each of the radiation pattern would be diverting in different directions, no issues. Now here the 4 elements are used. 4 elements are used with different sources for each of the elements. So yes, there would be 4 radiation patterns. Although the energy is very low, but yes, there are 4 radiation patterns. Now the 2 sources are here for 4 different elements, of making a pair of 2 each. So again, depending on the 2 sources, 2 radiation patterns are here. So it means as the number of elements increase, it is up to the user that how it increase the excitations. If you increase the number of excitations, your number of main lobes would be increased. Now, what will happen? It is very important thing to know that if we increase the number of ports, in suppose I have 64 elements, I have used 16 different ports with 64 different ports, and each of the 64 ports are fed with the same amplitude and with the same phase variations. Then what would happen? It would be the MIMO for 4G communication, that each of the element would be radiating in individual directions with a minute shift in the direction because of the similar properties. And once you try to join all these radiation patterns, it would be creating a donut shape again. So now here is the scene of MIMO technology for 5G communications, that there would be the phase variations in individual elements of 64 ports. By implementing the phase variation, using these phase shifters, now the 4 different elements are fed with the same source, but each of them are having the different phase shifters. Each of them are fed with the different phase variations. So each of them would be radiating in different directions and with different amplitudes. And once you try to recombine all these 4 elements, then yes, it would not be giving you the shape of donut, rather it would be giving you a much more focused beam into a particular direction due to the variations in the input phase shifts of the individual ports. So this is the figure. I guess this is the animation. Now you can see that this animation is giving you the glimpse that each of the element is radiating in individual directions, and if they will be combined, then it would be taking into a single direction. Similarly, you can have another view. Yes, you can have this particular view. This is the variation of the beam from one direction to another by introducing the concept of phase shifts. Since we have introduced the concept of phase shift, so these beam would be directed to different directions continuously. This is the concept which I used to prefer to call it as beam steering of 5G technology. And this was the concept of beam. This was initially the concept of beam forming in 5G technology. This is beam forming. This is beam forming, right? And this one is beam steering. These are the 2 technological advancements that are in the present scenario, and yes, you can work on that. So the very first thing to work in these domains is that you need to pick a platform where you can go for the simulation, right? For doing the simulation, there are ample of platforms, and the most promising one in the market is CST Studio Suite. It is a particular platform on which you can do anything into the RF and microwave domain, into the different applications of the domain. Either you are willing to have some antennas, or either you are willing to have some components, couplers, isolators, circulators, or you are willing to have some as biomedical application antennas, or willing to have some radar cross-sectional antennas. Whatever you are willing to do in the domain, you can do it on CST. And since I represent CST software, I was working as before the session, the introduction was given very beautifully, that I am working as an application engineer with the channel distributors of the solid systems who owns CST Studio Suite, and I am an application engineer on CST itself. So with the permission of the organizers, there is something regarding the licensing of CSG platform, as we all are from the domain of academics actually. So I'm just briefing you all about the academic licenses of CSG that we have. In CSG, there are a few type of licenses. The very first one is academic research license, in which you would be having a full capability of CSG Studio Suite. It is our main flagship product, which would be including CSG, all its solvers, plus an antenna makers. Antenna makers is a platform or a designing tool through which you can just create a model by just inputting your desired parameters. And along with that, you would be having a Spark 3D, which would be very useful while you go for the multifaction analysis or gas discharge analysis in particle domain. And along with that, there would be a FAST 3D platform as well, which is like for cavity-based designs, and an Opera platform as well, which is for low-frequency applications. So when I talk about full capability license of all these platforms, means you can do any sort of research on the platform depending over the configurations of the machines or the laptops you are working on. So in academic research license, we have three packages. The very first one is of single license. The second one is of 5 license, and the third one is of 25 license. We have, so you can directly contact us for having any of the license packs, or also to start your work to check the capabilities of the platform. You can also write to me for the evaluation license of this particular platform to start your work with. Thereafter, there is another package called CSG Academic Teaching License, which is a very beautiful bundle in order to enhance the interactions during the classroom teaching. Actually, it is of much cheaper cost, but yes, it is having some limitations in the mesh number of mesh cells. You can have some basic antenna designs, some horns, some patches, some reconfigurable antennas. You can also do some conformal antennas on the academic teaching license, and this would be very helpful in order to create the interactive teaching in the classroom. Thereafter, another package for the student that are planning to work on the designing part. This is CSG free student teaching license, free student license. Actually, it is very limited. It is just to give you the glimpse of modeling tools available in CSG. Its graphic user window, what does it have? So all these things would be there for you. If you are looking for some of the simulation tools, then you please do contact to me for any of the help. And yes, CSG, since CSG is owned by Dassault Systems, so pirated softwares are not allowed to use, and we would not be there to help you while you are working for pirated softwares. So this is all about the antennas for biomedical applications and MIMO technology. This was a very brief glimpse of everything that you can work on into the domain of biomedical applications and MIMO technology. You can start your work from today onwards by keeping these constraints, these parameters, these definitions that has been introduced to you guys. And I guess as time doesn't allow me to go in much more detail of this particular platform CSG, that's why I need to, I guess, with the permission of Dr. Prajul and Dr. Ponmani Raja sir, I will stop here. And for much more details, or for any of the CSG Studio design platform, you people please do contact me on the this particular mail IDs, right? On karthik@jyotimicrosystems.com or info@jyotimicrosystems.com, and you may please directly call me on the mentioned contact numbers. So this was all from my side, and it's my humble request to all of you to please do share your queries if there are any in the chat box, as we would be taking the queries from the chat box itself. So can I request Dr. Prajuan and Dr. Ponmani to please come in?
Yeah, tell me, sir.
So, sir, I guess this was all from my side for the session.
Yeah, thank you. Thank you so much.
And now I request the participants to please drop your queries in the chat box so that I can take the queries from
We'll share
their
your queries in the chat box.
There are few of the queries?
Yeah.
Okay.
How
Let me take
phase
that.
shift using CST? So one more
Pardon?
question. How
So
phase shift using
since
CST?
since voice is quite disturbing, so let me read out the queries since mine is in flow. in the chat box. So can you please read out the queries because I am not getting them. So, Ponmani sir?
Yes, sir.
Yeah, please read out the queries, please.
How to calculate ECC in terms of radiation pattern?
Sir, actually ECC is the concept, although it is a concept for having the mutual coupling idea of the radiation patterns, but yes, it is not calculated by using the radiation patterns. It is being calculated by two approaches. I guess I skipped that particular slide. Let me show you. Just give me a minute. Yeah, these are the two different approaches of calculating the different parameters of MIMO for 4G applications. The very first one is as parameter approach, and the second one is far field approach. So these two approaches are here for the calculations of ECC or diversity gain or multiplexing efficiency or mean effective gain. You can directly create such environment in the anechoic chamber, or before going to the fabrication level, you can just simulate it on any of the platforms available with you and can calculate it using the features available in the different platforms. We calculate these parameters using CST tool, and these are very appropriate with the measured results as well. Both the approaches can be implemented using CST. So using far field data, it is much more appropriate to calculate rather to use the S parameter approach, because as you can see in the S parameter approach, there are some antenna systems that are considered to be lossless, completely lossless, and it is also considered that all the antennas are excited with the same reference impedance of perfectly 50 ohms. So since by S parameter approach, the antennas are being considered as the perfect one, so we don't consider it. We just consider the far field data approach to calculate the ECC using CST platform.
So one more question: how pattern recognition is important in MIMO?
Pattern recognition.
Yeah.
Yeah. For pattern recognition, you can again use the platform CST, since all these radiation patterns can be visualized in CST, either it is for a single element or for the multiple elements. So you can first calculate the patterns for individual elements, and then you can combine it for the beam scanning or the pattern scanning of the complete structure. You can apply it using the flexibilities provided in the platform.
Excellent. Yeah. So one more question: how to calculate even mode and odd mode impedance of coupled antenna?
Sir, for that particular reason, you need to check the field patterns. As I already discussed in this particular design, let me show you where it was. Yeah, on this particular design, I discussed that with the help of field patterns, you calculate, you analyze the field modes, right? For different values, you try to calculate the field modes, and field modes can be easily calculated by creating the field patterns into the animation sort of thing. Once you try to animate the field patterns, then there you can see that how your electric field patterns are moving.
So any questions from participants? Where we can test SAR?
Where we can test SAR. There are many multiple premier institutions that are having that sort of anechoic chambers where you can calculate SAR. So you can work on that. You can contact any of the few of the IITs are here in India that are working on this particular thing. So you can do SAR calculation from there, or if you are asking in terms of simulation, then yes, CST is a platform where you can calculate or you can analyze SAR very efficiently.
Okay. Can you wind up this session? So now I invite our PG student Irene Jose to deliver the vote of thanks.
Good afternoon, all. I deem it a great honor to propose vote of thanks to all who have helped us in making this webinar such a resounding success. First of all, I would like to propose hearty vote of thanks to Mr. Rajendra Agarwal, Managing Director of Jyoti Electronics and Mr. Parth Agrawal, Technical Director of Jyoti Electronics, Ahmedabad, for all your wonderful support. Thank you, sir. I would like to thank our distinguished speaker, Mr. Karthik Goyal, Application Engineer, Jyoti Electronics, Ahmedabad, for making this webinar interesting and meaningful. I would like to thank Jyoti Management, Principal, our HOD, and all our staff members for all your moral support and guidance. We are also grateful to the coordinators of the webinar, Dr. Prajun P. and Mr. Ponmani Raja, for making this a great success. Finally, the wonderful participants who have turned up for the session from all over India. Thank you so much for your cooperation. Once again, I thank all for your cordial cooperation. Thank you.
Hello. Hello.
Hello.
Hello. Good evening, sir. Hello.
Hello. Hello.
Good evening, sir. This is Dr. Saidulu.
Yeah, good evening, sir.
Sir, I cannot receive the feedback link. Please.
So it is available in the chat box. You can check
Sir,
the chat box. I have just dropped it again.
I'm not finding the gym chat box actually.
I have just sent it again. Kindly check. Because it would not be possible to share it to the individual participants.
Actually, okay.
Kindly
Sir.
check the chat box.
Right, sir. Okay, sir. I found, sir. Okay, sir.
Good evening, sir.
Yeah, good evening, sir.
Are you providing any introduction course for students to learn basics of CST?
Sir, actually, we are connecting ample of webinars.
Okay.
During this pandemic situation, we have already done, I guess, 15 to 20 webinars on the very basics of CST and also on some a few of the advancements in advanced designs on CST. And we are having few webinars in the upcoming days as well.
Okay, sir. Where we can get the information, sir?
So you just contact me on my mail ID that is mentioned on the slide. You can just note it down. I am just dropping it on in the chat box. You can just write me and I'll drop you the registration links for the particular webinars.
Okay, sir. The student license available? Actually, students doesn't have.
Yes, student license is available from the website. I am also mentioning the website from where you can download the student edition by just registering. It is www.pts.com.
Okay, sir.
You can just go visit the platform, visit the website, and read about the platform, and can register and can request for the student license. Or thereafter, you can also request us for the evaluation license through your professor or through your guide.
Okay, sir. Sir, I need your mail ID.
I have just dropped Karthik at the in the chat box.
Yeah. Okay, sir. Yeah, sure. Okay. Thank you, sir.
So, is there any other query from any of the participants?
No queries, so we will wind up the session. So thank you, Karthik sir, your wonderful support and your wonderful presentation. The session was very useful and very informative. Thank you so much for your great support.
Yeah, thank you, sir. Thank you so much.
Thank you so much.
Yeah,
thank you all the participants for inviting everyone. Sorry, the connectivity is less. Thank you all for your attention. Thank you.
Hello. Hello.
Yes, sir.
Sir, how many days will take, sir? A certificate?
You will get it automatically, I guess. You will you just fill the feedback form and will definitely get back with the certificate.
I filled the field form, but I didn't receive it, sir.
Will receive, sir. Will receive. No issue. Will receive. Will definitely receive.
Actually, the e-certificate will be issued only for those who filled the feedback form. So you will receive your e-certificate from our IT section within the week. So this is a small announcement to the participants. So kindly note you will e-certificate received from our IT section within a week. Thank you.
Okay, okay, thank you. Hello.
Sir, hello, Karthik sir.
Yes. This.
Sir, in previous